In this video, I will go through the quantitative principles of computer design. Particularly, we'll introduce the two equations for evaluating alternatives. So far we have seen how to define, measure, and summarize the performance, cost, dependability, power and energy. So now we'll introduce some important observation of computer design and also the two equations for evaluating the alternatives. So the first observation is take advantage of parallelism. So at the system level, we use the scalability to refer to being able to expand the memory and the number of processors and the hard drives. And at the individual processor level, we take advantage of the instruction level parallelism. An important technique for exploring the instruction level parallelism is pipelining. And inside the one processor, we can also use multiple function units to parallelize the multiple instructions. The second principle is locality, which refers to the programs tend to reuse the data and instructions they have used recently. A widely held rule of thumb is that the program spends 90% of the execution time in only 10% of the code. There are two types of the locality. One is a temporary locality, which means that the recently accessed time are likely actually to be accessed soon. And the second locality is the spatial locality, which means that the addresses are near one another, tend to be referenced again. So the third principle is focused on the common case. So this is actually the most important and pervasive principle of computer design. So rather than actually making all cases fast, so we'll rather focus on the most commonly used and make it faster. So this principle works for energy as well as resource allocation and performance. So to evaluate how much faster overall in the system, we use the Amdahl's law. So which is actually expressed as the execution time of the old execution time times the fraction that can be enhanced. So that part we will find out how much actually can be enhanced as this term. And then for the non-enhanced part, we find out by one subtract the enhanced part, and together that's the overall factor. So then the overall speed up can be found out by using the old execution time over the new execution time. So then we can get the reciprocal of this whole term here as a overall speed up. As we can see here, the two important factors in the Amdahl's law is a fraction of the computation time that it can be enhanced and how much speed up we can achieve for that part. So now we'll see an example on how to apply the Amdahl's law to evaluate the enhancement. So here we assume we have a FP floating point square root is responsible for 20% of execution time of the critical graphics benchmark. And then there are two proposals for improving the performance. One is to enhance the FPXQR hardware and speed up its operation by a factor of 10. The second is to make all the floating point instructions in the graphics processor run faster by a factor of 1.6. So the floating point instruction is responsible for half of the execution time allocation. So now we need to compare the two design alternatives. So for each option here, we can use the Amdahl's law to find out the overall speed up. So for the first option, the FPSQR part, the portion which can be enhanced is 20%, and then the factor is 10, and then the non-enhanced part is 1 minus 20%. So together we get the overall speed up as 1.22. Then for the second option, the portion that can be enhanced is half of the execution time. So that's 50%. The factor is 1.6. Then the overall speed up is 1.23. As we can see here, making all the floating point instruction faster is actually slightly better than only enhancing the floating point square root function. We can also use m.law to find out the improvement of the reliability of the whole system. So using the previous example of the disk subsystem, which has 10 disks and the disk controller and also power supply. Now assume that the power supply part can improve the MTTF via redundancy from the 200,000 hour to 380 million hour MTTF, so which is 4150 times better. So now how much is the overall improvement on the reliability? So to use the Amdahl's law here, we need actually be clear on how much portion of this power supply reliability over the whole system reliability. So we can find out that again using the failure rate part, because the failure rate is as assumed before, it actually can be the summation of the failure rate of each component. So that's kind of like a summarizable. So now the failure rate is still calculated based on the summation of each component's failure rate. So the total failure rate is 17,000, and then out of that we have the power supply part is the last portion, so which is about 5/17. That's a portion, and then we can find out the factor can be improved on the reliability is 4150 times. So then we put into the Amdahl's formula, we can get the overall improvement on the reliability as this 5/17, that's the 29% portion of the system's improvement, and the improvement factor, and then the non-enhanced part. So together we get the improvement of the reliability of the whole system is 1.41. Next, we'll look into the principles of the computer design, and particularly in the processor performance part. So the processor performance, we can use the general formula of the CPU time as the CPU clock cycles for a program times the clock cycle time. So the clock cycle time can be replaced by the reciprocal of the clock frequency. Sometimes we're given with the clock cycles per instruction, and so then we can obtain the CPU clock cycles for a program as the product of the CPI times the instruction count. So then putting back to the CPU time formula, which can be expressed as the product of the instruction count, CPI, and the clock cycle time, or either expressed in this unit way. So next we'll look at what are the impacting factors to these three basic terms. So this table lists the factors. So starting from the bottom to the up, we'll see each one by one. So the technology kind of determines the feature size, so which actually will impact the implementation. So that kind of actually definitely impacts the clock cycle time. But then does that impact the CPI and the instruction count? So actually those are more related to the organization and instruction set architecture. So those are not impacted by the technology. The core organization is also related to the implementation. So it will impact the CPI as well as the clock cycle time, but not the instruction count. And the instruction set architecture will impact definitely the CPI And also, if you have a more complex instruction set architecture, you have more, it will kind of impact the clock cycle time and also the instruction count. And the compiler technology will kind of like use some techniques to reorganize the code, and also it will actually parallelize some of the code by using loop parallelism. So this actually will definitely impact the instruction count and the CPI, but not the clock cycle. Then the programming language also will make a difference in the instruction count and clock cycles per instruction, but not the clock cycle time. And on the top level, the algorithm, of course, if you pick more parallel algorithm, then you have actually end up with a shorter code length. So then your instruction count is impacted, and also it will also possibly impact the clock cycle per instruction. So next, we'll see how to calculate the CPI. The calculation of the overall effective CPI is done by looking at the different types of instructions and their individual cycle counts and averaging them. So in general, we use the summation of the instruction count for each instruction class times the clock cycles per instruction for that class, and then divide by the total. So we can also put into the other way by using the instruction count percentage times the CPI, and then get the sum of them. So the ICI is the instruction count for each instruction class I, and CPI is the clock cycle per instruction for that particular instruction class. N is the number of instruction classes. So next we'll see an example of calculating this using the CPI to compare the processor performance. This is actually the same example as we did using the Amdahl's law, but now we actually expressed in the other way. So here the frequency of floating point operation is 25%. Average CPI for floating point operation is 4.0. Average CPI for other instructions is 1.33. And then the frequency of the floating point square root function is 2%. And CPI for FP-SQR is 20. So now we have two design options. One is to decrease the CPI of the FP-SQR to 2. The other one is to decrease the average CPI for floating point operations to 2.5. Now we need to compare the two design options. So here we use the CPI to calculate the the improved CPI. So the original CPI is obtained by using this summation of the two types of the instructions: the floating point instructions, CPI 4, and the 25% of instruction, and then non-floating point, and it's 1.33 times that percentage. So the original CPI is 2.0. Now for using FP-SQR, then we can find out the new CPI by using the original CPI, subtract that reduction part. So that part is the FP-SQR portion, 2%, and then reduction is from 20 to 2. So then we get the new CPI as 1.64. And then for the floating point improvement option, we take that we use the general formula. So 75% of the non-floating point CPI no change, and then the floating point CPI changed to 2.5. So we get the new CPI is 1.62. So then just from the CPI comparison, which one is better? Actually, the new FP is better, right? From the number, we can see that. So then we can find out the speed up of a new floating point instruction by using the original CPU time over the new floating point CPU time.
The basic way to compare the performance is using the CPU time formula. So here we plug in the CPI original and CPI new FP, and then IC and clock cycle time are same. So then we find out the speed up using new FP instruction is 1.23. So using the same formula, we can also find out the speed up for using FPSQR is about 1.22. So then the new FP instruction has a slightly better speed up. So compared to the previous example, we got the same answer as using Amdahl's law. So in the homework, you have there are some similar questions. You can use either the basic CPU time formula or either using the Amdahl's law to analyze the speed up. So if you have any question, please let me know.